the central limit theorem. From a population of n returns, capital N, the population is called A. So R1, 2, 3, 4, 5, 6, 7 to capital N. We randomly select n returns to form the sample B. RB1, RB2, 3, 4, 5 to N. RB2 could be R3, RB3 could be R1048, RB1 could be R51. Okay, RB1, B2, B3, B4, and so on have been randomly selected from A. Okay, so they don't necessarily follow the same order in B as in A. From B, we can calculate a sample mean, so the average of the values in B, and we can calculate a sample standard deviation. Okay, so the sum of all elements in B minus sample mean to the power 2 divided by n minus 1 to obtain a non-biased estimator of the true standard deviation of the population. Good. We create a new sample of n observations randomly picked from A. We call this sample C. C, RC1, C2, C3. As for B, C1, C2, C3 can be anything from A. They have been randomly chosen, so they don't necessarily follow the same order as the order at which they appear in A. The sample mean of C is given by the sum of all items in C divided by n, all good. Before we compute the sample mean for C, and even before we collect C, the central limit theorem gives us a possible range of values for the sample mean of C. So the central limit theorem, so when n is sufficiently large, there is a 95% chance that the sample mean we would compute with a new sample of the same size would be between the sample mean of B minus 2 times the standard error of B and the sample mean of B plus 2 times the standard error of B. So R minus 2 times SB over square root of n are, so these are the limits, like the lower limit, the upper limit of an interval. Each time we create a new sample of size n from A, so 95% of the time, the sample mean we will calculate from this new sample will lie within these two, between these two values. So the central limit theorem. So if we just calculated a sample mean R over line and a sample standard deviation S from a sample of size n being sufficiently large, then we are 95% confident that the sample mean we would calculate from a new sample of n items coming from the same population lies in the interval sample mean minus 2 times standard error plus n sample mean plus 2 times standard error. That is, if we take a sample of past observations from which we compute a sample mean R over line and a sample standard deviation S, then the interval R sample mean plus or minus 2 times the standard error is the 95% confidence interval of the average return we should expect in future samples of size n. Why is that? It's because whatever the distribution of the items from which the sample is created, the average we obtain has a symmetric distribution, which is very close to the normal distribution. And with the normal distribution, elements of a normal distribution have 95% chance of being within such an interval.